The last type of conic we're going to look at is the hyperbola. And the definition of a hyperbola is the set of points in a plane where the difference whose distances from two distinct points are constant. With an ellipse, we had the sum of 2 points that were constant. Now with the hyperbola, we're looking at the difference. So in this, we're going to have 2 foci, and we're going to have 2 graphs that sort of look like parabolas. So here's the general form of what your hyperbola is going to look like. You're going to have 2 pieces. So we're going to have 2 vertices that we find. And then inside each of the vertices, you are going to have a foci. And if I were to find the difference between these 2 points, it is going to be a fixed constant. And by difference, I mean if I were to draw a line out from a graph, or from the foci to the graph, then down to the other foci, subtract those 2 differences, it's always going to be the same. And just as I did with my ellipses where I had a horizontal and a vertical version, same thing is going to be true with the hyperbola. I'm going to have a horizontal and a vertical version. Now I made the comparison to the ellipse already, where the ellipse is the sum of the distance between 2 points called foci, and hyperbola is the difference between 2 fixed points called the foci. So it probably tells me that my formula is going to look very similar to that of an ellipse. If you remember from an ellipse, the way it looked was x squared over a squared plus y squared over b squared is equal to 1. This was the ellipse. Now the case is going to be with the hyperbola, I'm going to have x squared over a squared minus y squared over b squared is equal to 1. Now we're going to have a subtraction sign in between. So the only thing that's going to be different between the ellipse and the hyperbola is the fact that I've got this minus sign in between. So I'm going to have an x squared and a y squared, but there's going to be a minus sign with one of the terms. The other piece then is where do the a's and where do the b's go? Because remember, that's an important part of what we talked about with an ellipse. Well, with a hyperbola, the a squared is always going to be the first denominator. When we had an ellipse, the a squared was always under the piece that had the major axis. So sometimes the a was under the first fraction, sometimes it was under the second fraction. With the hyperbola, the a is always underneath the first fraction. So here, since this is opening in the y direction, my equation for a hyperbola is going to be y squared over a squared minus x squared over b squared is equal to 1. The first fraction is going to tell me what direction the hyperbola is going to open in. And that's the piece that's always attached to the a squared. So here it's in the y direction. My second equation right here would be x squared over a squared minus y squared over b squared is equal to 1. Once again, notice the a squared is always going to be the first denominator of the hyperbola, and the a squared is underneath the x squared, which tells me it's going to open in the x direction. If I were to have some shifts involved, y minus k quantity squared over a squared minus x minus h quantity squared over b squared is equal to 1. H still goes with x and k still goes with y. It does not change so that h is first and k is second, but h is always tied with the x. And then the horizontal version, x minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1. A couple of facts about hyperbolas. Each hyperbola has 2 asymptotes that intersect at the center. That's how I determine what the center is. It's where these 2 asymptotes intersect. If I've got no shift, the center is at 0, 0. If there's a shift, it's elsewhere. The midpoint between the 2 foci is also the center. So you know the distance from the center to the foci are the same. The points at which the line segment through the foci meet the hyperbola are called the vertices. And the line segment joining the vertices is called the transverse axis. So that's the line that joins these two vertices right here. In both cases, A is the distance from the center to the vertices, and C is the distance from the center to the foci. That is key. Just like we talked about with the ellipse, the C is the distance from the center to the foci, and A is the distance from the center to the vertex. Exact same case is true with the hyperbola. We're talking about distances. And then finally, eccentricity is once again C divided by A. However, with a hyperbola, the eccentricity is always going to be greater than 1. With the ellipse, it was always between 0 and 1. And the larger the eccentricity is, the closer the branches of the hyperbola are being to a straight line. Back when we talked about ellipses, the closer to 0 we were, the more circular it was. The exact opposite was as we get closer to infinity, the more of a straight line it becomes. So the bottom of page 154 is going to show us 8 things that we need to do when we look at graphing a hyperbola. And we're going to graph in the next example. But a couple things I want to point out here is that my vertices is going to be in the format c squared equals a squared plus b squared. That is different from what you had with the ellipse, where it's a squared minus b squared. Vertices of a hyperbola looks just like the Pythagorean theorem. And the other part is that the vertices always are the square root of the first denominator. Remember, a squared is always, always, always the first denominator. So it just determines, is it the x piece or the y piece? And I've got to be careful how I say it's always the first denominator. It's probably better for me to say it's always the positive fraction, but when we're in standard form, the positive fraction always comes first when we're talking about hyperbolas. So in the next part, we're going to look at how would we graph these hyperbolas.